last lecture.
Yeah.
So I just want to quickly give some information before we talk about the topic of the day. So this is and you can take it as a mock exam. So I prepared the exam and I'm going to show you the template with which it's done. It will be posted to Canvas. You can expect something similar on Tuesday. Okay. So calculator is allowed, closed book, closed notes. Okay. So no, you don't have to bring any sheet, any book, anything. Whatever information you need for the exam is provided in this exam itself. Okay. 4 problems all have equal weightage, just like usual. So if you see here, the first problem is going to be solving a first order ODE using RK4 method. And I've provided the RK4 method right here. So all you need to know is how to calculate these functions, how to do this methodically without making mistakes and getting the answer. So the formula you need is provided right here. Okay. So if you see the demo or the problem that I have here, solve the following differential equation from t equals 0 to 1 using a step size of 0.5. That's basically asking you to solve it at 0.5 and 1.0 with the initial condition y of 0 is 1. You can easily integrate this equation and get the exact solution, which is exponent of minus t squared. And I'm even telling you a hint of how to cross check your answer. Okay, right here. So you need to fill out this table at 0.5 and 1.0, compute the exact value also, and then get the absolute error. So you need to fill out 1, 2, 3, 4. 4 numbers that we look out for. Okay, so I'm not asking you to memorize anything. Again, all I need you to do is be able to use this formula. Second problem, we are solving a system of differential equations using Euler's method. So this is nothing but Euler's method is very simple, as you know. It's just a one-step method where you take the value of the function and then multiply it with the step length h. So you need to solve these two simultaneously. Actually, yesterday at the optional recitation session, I did this example from start to finish. So if you have a chance, please watch that recording. Okay. Again, you're asked to fill out this table. Here is t equals 0 initial condition, 0.1, 0.2, 0.3, y and z, 6 values. The catch is, do not think that you could first solve for y and then solve for z. That is the most common mistake you could do. They have to be solved simultaneously at each time step. So at 0.1, you have to calculate both y and z before moving on to 0.2 and 0.3 and so on. Okay. So again, the formula you need is right here. And for statistics, for those who have been paying attention in class about what is mean, standard deviation, and what is this confidence interval or standard error estimate, all this information is not critical because I just put it here, useful information. You don't have to read it in the exam hall. But for doing this problem, you need to have this table, and that is required information. So if you see at the top there, I put required information. So the table is provided to you, and the problem here reads like, the confidence interval around a sample mean value is the range in which the true value may be found with a certain probability. That is basically the definition of this confidence interval. For a data set with a standard deviation of 3% of the mean and a sample size of 9, calculate the confidence interval or standard error estimate as a percentage of the mean at 95% probability. This is just like a placeholder problem. I will of course not ask the same thing literally on Tuesday, but to give you an idea of what you are expected to know, you should be able to use this formula, look up the t statistic value from the provided table. That making sense? Yes?
Will we be given all the formulas?
Yeah.
Or did I just?
You missed it. I know it's very polite to say, oh yeah, sure. Anyway, so this is right here. Sx is what we take as the Sx divided by n. So everything you need is right here. Okay. So that is T statistic, which is statistics of small data sets. And then problem 4 is related to Gaussian distribution, which we will discuss today. So what is Gaussian distribution? Quick snapshot of the bell curve, and within one standard deviation is 68%. We'll see that today. Within two standard deviations is approximately 95.5%. So all that is given to you, sort of like a refresher. And then the required information is this table, which we will see how to use today. And you'll need to look up values from this table. And we'll do one example. Actually, we'll just do this very example that is in the that is given here. So we'll try to solve this by end of class today. So to be clear, it's closed book, closed notes. Don't bring any material except calculator, and all the information is self-contained within the exam. Okay. Yes.
So there's going to be the exact problems on that, or is it going to be similar problems?
Similar, not exact. If I tell you these 4 and ask the same 4, what happens to your integrity? Forget mine. What happens to your integrity? Sorry. That is true, but also it would be very I don't know. It would be not be correct. Anyway, jokes apart, you can expect something similar, not same. Yes.
Okay, so on here, the standard deviation notation is sigma x.
Yes.
But in the handout, the standard deviation notation is Sx. Like when.
Okay, so you want something that is consistent.
Yeah.
I'll type this up and I'll make sure this exact thing appears.
Okay.
So that there is no confusion between, if you are following this, you'll be able to do it. Yeah, thank you. Yeah.
Do we get extra credit if we dress up on exam?
No.
So let's start with that. Are you going to post this?
Yes, I'll post this right after class. So this is like a mock exam which you can try and see if you can finish this in 80 minutes. Yeah.
Is there a solution to it to test?
I will solve this now. I already solved the ODE problems during the recitation yesterday, which you can go back and watch the recording. So just one more problem here that needs to be solved, which we'll do.
Did you solve problem 3 yesterday too?
Problem 3 is really straightforward. If you see it, it's just plugging the formulas in here. If you want, we can do it at the end of class. I at the recitation yesterday, which 2 people attended, we were able to cover 3 examples. One related to this, one exactly this example, and then one more example similar to this, and then one example in which we talked about a second order differential equation. So if you actually watch the recording, you will see any second order differential equation of this form, a function of t, y, and dy by dt, is also something that reduces to a system of 2 equations, which if you know how to solve this, you can also know how to solve the second order ODE. So for those who could not make it yesterday, 2 things: please watch the recording and also try to make it to the remaining 2 sessions via Zoom. Okay. And tomorrow we'll go over some examples on statistics. Can we move on? I'll post this. Thank you. All right. So now there was one. The other is exam 2. The scores have been posted. TA will be distributing the exams at 12:35 p.m. today. And homework 3, you can collect it from the TA's office, Friday 9 a.m. to 11:30 a.m. His office is ES 327. And homework 4, you can collect it Monday, 9 to 11:30 a.m. And homework 5, Wednesday, 9 to 11:30 a.m. By the time, we'll also try to return homework 6, but somehow by Thursday, you'll have your homework 6 also. So just give us a little more time to get you homework 6, but you can go pick up this tomorrow, okay?
Is it okay if we just show up on Wednesday and get all?
Yeah, that's fine. That's up to you, but we want to make this available in this order.
If we can't visit any of those like 9 to 11:30, would they be like in an office or somewhere that we could pick up?
You can email the TA, CC me and ask for a time. The TA will provide you a time, maybe he'll just meet with you at 2 o'clock, hand you the exam. So, we'll work something out.
I could also pick it up.
No, we will not give your work to anybody else other than you.
If I say it's okay that you can pick it up, I like write it out. express
You
it.
give it in writing, then we'll figure it out. All right, so that said, let's continue on to today's topic. Just trying to adjust the focus here. So this information, you want to hold on. Whenever you are given a problem and asked to calculate confidence interval for samples that are smaller than 30, this is what you will use, okay? So for those who could not come last lecture or the one before that, maybe quickly I'll try to solve that problem in the mock exam, and maybe you can see the formula being used. So to Blake, your point, problem 1 and 2 refer the recording from yesterday. Problem 3 and 4 we'll solve today now, okay? So what does the problem say? For a data set with a standard deviation of that is 3% of the mean, okay? So I'm going to write for this data set, the number of observations is n equal to 9, that's given in the problem. The standard deviation is 3% of the mean. So that is like writing 3% of the mean. That is like writing 0.03 times x bar, or sigma x divided by x bar equal to 0.03. Okay, 3% of the mean. Calculate the confidence interval or standard error estimate as a percentage of the mean. You are not asked to calculate it in absolute terms. You just have to calculate it as a percentage of the mean. So this is a confidence interval where you have the formula T multiplied by sigma x equal to square root of n. So your T value, which we look up now, multiplied by sigma x, which is 0.03 times x bar, divided by square root of n. N is 9, so square root of n is 3. So the next step is, most of the work is already done. You need to be able to read the problem statement, distill out what the standard deviation is, how many observations are made, put them into the formula, and then you need to look up the t statistic value, which you can look up in the provided table. So at 95% confidence, and what value of nu should you look up? We should do 8. That is, we talked about this last time. nu is called the degrees of freedom. And this is always 1 less than the number of observations, so it has to be 9 minus 1 or 8. So if you look up the table for nu equals 8 and probability level equals 95%, what is our t value? 2.306. That is 8 degrees of freedom and 95% confidence, 2.306. .306. Okay. .306. So now the remaining step is for you to put this number into the formula and compute the next step. I'm going to so confidence interval CI is t statistic, which is 2.306 multiplied by 0.3 x bar divided by 3 0.03. So I'm asked to find out the confidence interval as a percentage or fraction of the mean So I need CI divided by x bar, which is 2.306 multiplied by 0.03 divided by 3. So that is nothing but 0.02306. So, or in other words, the CI is 2.3% of the mean. It's 2.3% of the mean. So this problem did not involve actual numbers. It dealt everything in relative proportions. Finally, to give you the CI as a percentage or fraction of the mean. Of course, the more common variant is to give you a standard deviation as a number and then use that here so that you can compute x bar plus minus CI with 95% probability. And this is the interval that contains the true value with 95% probability. So you might be given like a statement saying the true value, it lies between x bar plus CI and x bar minus CI with 95% probability. That's the final statement, and you might be asked to fill out certain missing words from that statement. That is all exam related stuff. As engineers, when you're trying to design measurements or design studies or observations, our goal is always to make this CI as small as possible. Why? So that you can talk about your true value with more certainty. Okay, and how do you make this confidence interval smaller in practice? If you look at this formula, what clues can you derive?
More observations.
More observations is the surest way to shortening or to narrowing this interval to as small as you can or want. Okay, so that is something to keep in mind. Of course, that making more observations doesn't happen all the time free of cost. It has to be balanced against other constraints that may exist. Okay, all right. So now we want to talk about estimating confidence intervals or true values in large data sets, or if we also use the word large populations. And an ad hoc cutoff is n greater than 30 is considered large. Yeah,
Is this, the problem 4?
this is problem 4. Yep. And in the exam, you might not be given an indication saying this is small data set, this is large data set. You will just be given the number of observations and you have to decide based on that, okay? So we talked about one very simple quantity like height, and we did a survey of what are the heights in this classroom where we have about 30 students or 30 people. So if you do this for a large number of observations, that is, if you take a survey of hundreds of people, you can get a mean value, which is always okay. I'll start with raw data. How does the data come in when you make the observation? Suppose you're surveying heights, it will be height 1, height 2, and let's say you survey 1,000 people, so it is 1,000 height values. And from this, you can always compute what is the average value. 1 over n, sigma xi, I equals 1 to n. You can have 100 or 100,000 data points. This is just arithmetic average, okay, very easy to compute. You can also compute the standard deviation, which is defined as 1 over n, not n minus 1, I equal to 1 to n, xi minus x bar whole squared square root. So this is called population mean and population standard deviation. You don't have to worry too much about why it is n and not n minus 1. If n is a large number like 100,000 or 1,000 or so, n minus 1 and n don't differ by much, so they're practically kind of close to each other. So we just don't use n minus 1 here. So you have this mean and standard deviation that are easy to compute. The idea is if you take a mean value, okay, and you divide the possible values into bins. We talked about binning. If you divide them into bins, okay, and you start putting down the number of objects or number of people with a certain height range, you are going to get a distribution that looks like this. And so on. So this distribution, whenever you do this for large population, whatever be the quantity being measured, it is, note this statement, it is commonly observed that such a distribution follows a normal distribution function, which looks like this. The normal distribution is 1 over sigma x times square root of 2 pi exponent of x minus x bar divided by sigma squared times half. So this function, the solid line that I write or that I draw here, is described by the function, and the dashed lines are the actual number of objects that you count in each bin. Now you recall that example we did in this class, we divided around 31, on that day I think we had like 23 people. So those 23 people, their heights were put in 3 bins, 5 to 5.4, 5.4 to 5.8, 5.8 to 6, and 6 to 6.4, so 4 bins. 3 bins? Okay, 3 bins. So that was a small population, but what we generally do for large populations is that any type of data that you get, you can summarize it using this distribution, based on two parameters that come from the data, the mean and the standard deviation. Yes.
Sigma X and sigma, are those the same thing or?
X and sigma.
Sigma.
Yes, and then there's a
Oh, yeah,
exponent.
let me rewrite this. So exponent of minus 1/2 x minus x bar over sigma x squared. So this function is called the famous Gaussian or normal distribution. Gaussian or normal distribution. Mathematically, it's sort of messy, okay? It's you don't want to do integration on it, it's complicated, but it has some very interesting properties that we can use. Okay, so let's consider the special case where x bar equal to 0 and sigma x equal to 1. That is, you can always think of some quantity which has a mean of 0 and standard deviation of 1. This special case is called the standard normal distribution. Standard normal distribution. So this has f of x equal to 1 over square root of 2 pi multiplied by exponent of minus x squared over 2. Why it has simplified from here? Because I take this function and apply x bar equal to 0 and sigma x equal to 1. And the value of x ranges from minus infinity to plus infinity. Okay.
Is that negative x squared, negative xi squared?
Negative x squared.
Like X bar, just X.
Sorry.
Is it not? It's not X bar, it's just X.
X bar is 0. We set x bar to 0. Yes.
Will X bar and sigma X be given or no?
They will be given. See, at the end of this discussion, what I'm going to say is any problem which has a value of x bar and sigma x can be reduced to the standard distribution for which we have a lookup table. So instead of computing every problem from scratch, we will reduce every problem to the standard normal distribution and use the lookup table. And one of the handouts in the exam is the lookup table. All right, some properties. Okay, so if you think about all the possible outcomes, that is, if you take this curve, okay, I'm going to redraw that for the standard normal distribution, where this is 0, and this is x-axis, and this is f of x. Okay. If you plot this function, it will look like this. Okay. That's not very symmetric. It has to be symmetric, but I can't draw well even if my life is at stake. So the area under this curve, okay, the area under this curve, under the curve, represents something. what would be that? It is, if you think about a dice, for example, what is the chance of getting a 1 if it's a 6-faced dice? 1/6. You can think about what is the chance of getting 1 or 2, that is 2/6. What is the chance of getting any number in a dice? 1, right? It's a certainty. That is, if you sum up the probability of all the outcomes, P1 plus P2 plus up to P6, that should add up to 1. In terms of distributions, the area under the curve represents all possibilities. So if you integrate this function from minus infinity to plus infinity, you get 1. Okay, so this square root of 2 pi is added to ensure that this integral is always 1 if you integrate it from minus infinity to plus infinity. And I also said that it is symmetric. That is, if this whole area is 1, this area is 1/2 and this area is 1/2. So this implies 0 to infinity f of x dx is equal to 1/2. Okay. Now, if I think about, say for example, 0, or if I think about any two values, say a and b, the integral from a to b of f of x dx represents or is the probability that x takes values between a and b. Now we'll come back to that height example. What is the chance of any one person having a height of 5 feet 4 inches? Exactly 5 feet 4 inches.
How accurate is your resolution?
You can never measure anything, or you can never measure anything down to like full accuracy. With that said, since height is a continuous number, 5 feet 4 can actually mean 5 feet 4.005, which means any one person getting exactly 5 feet 4 is 0. It is like asking, what is the probability that x has a value exactly that is equal to a? So if I ask that value, integral a to a f of x dx, you don't have to be a math expert to say this. What is the value of this integral? Is 0. It's like asking what is the area of a line. So what is the area of this line? 0. What is the area under this curve? It's between a to b f of x dx, and that is the probability that x assumes values between a to b. A to b. So if you want to generalize this a little bit, 0 to x f of x dx, a 0 to x f of x dx. This is 0 and this is uppercase x. I just want you to qualitatively tell me what is the value of this integral if x equal to 0. Just look at this picture and tell me. X equal to 0, x equal to x.
The infinity?
0 to 0 of a function. That should just be 0, right? That's like the area of a line. So that is 0. And what happens when x equal to infinity? That is, you place it all the way at infinity. Sorry? No, I'm saying the position, the area under the graph up to infinity. That doesn't make the area itself infinity. See, this area stretches from 0 to infinity. That is, initially it is large. As you go further and further, it becomes smaller and smaller, but they all add up to 1/2. So if I place my other slider at infinity, how much area am I covering? 1/2. right? So this is 1/2. Between 0 and infinity lies reality always. In reality, no quantity is like 0, no quantity is typically or actually infinity. So this quantity here represents the probability that x is less than or equal to uppercase X. Okay, this is an important statement here. Just like this one, where all I've done is to take this statement, put a equal to 0, b equal to uppercase X, and I have this here. Okay. Now, it won't be very convenient or useful for us to keep computing this integral all the time. And that is why, like I said, we have the lookup table where this integral has been computed for values of x, uppercase X, from 0 to something like 4 or 5. Because practically after that, this function converges to half, so you don't have to keep computing. And you'll see that when I pull up the table. So give a pause for the writing. Once you understand this table, this can actually be a lot of fun. And problem 4 is the problem you might be able to do with least sweat. Okay, if you actually understand this table. So see here. So if you look at this bell curve, there is the mean, which we took as 0, and then there is one standard deviation on either side. So we want to see if we can recover these numbers from that lookup table. Okay, just we'll come back to this, but we are going to see how much area lies between one standard deviation, between two standard deviations, between three standard deviations. And I'm sure you have heard of this word 6 sigma somewhere in manufacturing. Can anyone tell me what you understand as 6 sigma? 6 sigma protocol is typically given for process engineering, wherein you try to do quality control to the extent that you predict that the rate of failure is only 1 in a million. And that number 6 comes from, if you actually estimate this, how much area is between 6 standard deviations, it will be 1/1,000,000 of a percent, or 99.99999%. That is one short of 100%. That is 1/1,000,000th short of 100%. Anyway, we'll come back to this. Okay. So look at this table here. So on the top, it says 1 over square root of pi, 0 to z1, e power minus beta squared over 2 d beta. I used the notation x, they are using beta, and I used uppercase X, they are using z1. Okay. If z1 value is 0, the integral's value is 0. If z1 value is like 3.0 or it's like 3.09, we are almost fully at 0.5 value. And if you see the picture below, the shaded region is the value here. That is, when z1 is 3.09, the shaded region has an area of 0.5. Okay, so all we have to do is learn how to read this table, and I'm going to give you like a series of quick fire lookup exercises to do, and you're going to look up and tell me the numbers. Okay, so I hope you have your laptop with you, or I'll leave this on the screen so that it might be hard. Yes.
What did you say that you wrote for beta?
I used X, they are using beta.
Okay, and then for Z1.
I used uppercase X, they are using Z1. Yeah. All right, so I want you to look up So I want you to look up 0 to 1. So I'll write it in their notation. 0 to z1 equals 1.0, 1 over square root of 2 pi, exponent of minus beta squared over 2 d beta. So from the table, what is this value? 0 to 1, 1.0. Point 3413. 0.3413. You can do this for 0 to 2. 0 to 2 will be 0.4772. Now comes the actual question. What about 1.0 to 2.0 square root of 2 pi exponent of minus beta squared over 2 d beta? Before you tell me anything, what is 0 to 2? Geometrically, what does it represent? It represents the area between 0 and 2. So here is 2, it represents this area. Yes,
Would it just be the middle value of 0.3413 and 0.377?
not middle, difference. That is 0 to 2 represents this area, okay? 0 to 1 represents this area. So if you want 1 to 2, it's literally subtracting 1 from 2. So are you able to see this geometrically? You just have to calculate 1 to 2 is representing this area, which is, you can write it as 0 to 2.0 minus 0 to 1.0, which is 0.4772 minus 0.3413. 0.1359. 0.1359. Thank you. So now you just have to do this little carefully, and it's actually very simple to read. That's what I'm going to try and do with that example coming up next. Okay. So maybe the space isn't enough for me. All right. If I want the probability that x lies between 1 to 2, I will look up 0 to 2 minus 0 to 1, and that answer is 0.1359. We just did.
And we multiply that by 100 per percent, right? It's not.
Yeah, the scaling part we'll get to it, but this is the probability. Suppose I want to know what is the probability that x is greater than 1.5. How will I define that probability? X can take anything from 1.5 to infinity. Yeah.
There we go.
Yeah.
Assuming you want to do like you want to figure out 1.5 into the values.
Yeah.
So you do this sort of subtraction.
Yeah.
So you're gonna do.
Subtract what from what? Yeah.
I know you're gonna subtract 0 to 1.5 from.
0 to infinity.
Yeah.
So yeah, you want to say something?
0.5 minus whatever the value is at 1.5.
Right, so that is this x greater than 1.5, you can also write 1.5 greater than x greater than infinity. So this is like writing 0 to infinity minus 0 to 1.5. But 0 to infinity, you know the story, that's half. So half minus, what is for 1.5? 0.4332. 0.4332. How much is that? 0.5 minus 0.4332.
0.0668.
0.0668. So let me turn off the screen share for a second, make sure this is getting recorded. This is nice to see on the recording. So if I ask you to shade the area that is represented by x greater than 1.5, what will you do? You draw the bell curve. Draw the bell curve. And here is 1.5, let's say. Everything between 1.5 to infinity. Okay. So we saw first the area under the curve is 1/2 from 0 to infinity. We saw the first thing is from 0 to infinity, the area under the curve equal to 1/2. If we want x between A and B, that will be 0 to B minus 0 to A. Okay. And if you want x greater than C, that will be 0 to infinity minus 0 to C, which is nothing but 1/2 minus 0 to C. Okay. Now I want you to use the table to tell me what is the probability that x takes a value between -1 and +1. First, let's shade it. Do the shading first to help you visualize this thing. So I want to know, here is the bell curve. Let's say here is -1 and here is +1. I want to know what is the area under the between these two vertical lines.
Would just be 2 times the integral from 0 to 1.
2 times. So what he is saying is the vertical line x equal to 0 divides everything into equal halves. So this left hand side area should be equal to the right hand side. So he's saying this -1 to +1 is nothing but -1 to 0 plus 0 to 1. -1 to 0, yeah.
Will it have the same number, just be negative?
No, it should be.
Area is always a positive number. Area can't be negative. That is, this integral can't be negative. So this is -1 to 0. So that is like if you hold this as a pivot and flip the page, this will be nothing but 2 times 0 to 1. Mathematically speaking, look at this function. Is this an odd function or even function?
Even. Or wait.
What is odd? What is even? So if you have a function and you consider f of minus x and that is also equal to f of x, this is a even function. If you have f of minus x and this is equal to minus f of x, that is a odd function. Example is this. Take y equal to x. The graph looks like this. So if you have minus x, so -1, the value is -1. If you have +1, the value is +1. So this is an odd function. You get like a inverted mirror image. if you take the function, for example, y equal to x squared, whether it's -1 or +1, you get the same value. So this will be an example of a even function. So what you have here is an even function. So what that means is something between -1 to +1 is equal to 2 times 0 to 1. This is easy enough. What if I say I want to know the area between -1.5 to +1? How will you split this? And the goal is not to do integration. The goal is to avoid integration and use the table. So how will you split this?
Would you just split it at 0 and do your value of 0 to 1.5 and 0 to 1?
So you can write this. First of all, this is obvious. Everybody would agree with me, right? 0 to 1 is obvious. Your table can be used directly to read 0 to 1. You're with me? -1.5 to 1 or -1.5 to 0. In your mind, I want you to put a ruler or put your hand here and flip the page about your hand, so that this is just projected as 0 to 1.5 to +1.5. So this is nothing but say -1.5 to 1 of 1 over square root of 2 pi exponent of minus beta squared over 2 d beta is nothing but -1.5 to 0 plus 0 to 1. No need to modify anything. This can directly be looked up. Look up. This one -1.5 to 0, 1 over square root of 2 pi exponent of minus beta squared by 2 d beta. For those who that feel this geometry is a little unsettling, I'll give you mathematical explanation. Set beta equal to minus gamma. So d beta is minus d gamma. I'm just transforming the variable of integration, so that wherever beta appears, I have to replace it with minus gamma. So if beta is 0, what is gamma? Also 0. 0 minus 0 or nothing but 0. And then 1.5 or minus 1.5 becomes minus of minus 1.5, which is 1.5. So I have 1.5 to 0, 1 over square root of 2 pi, exponent of what is minus gamma whole squared? That is again gamma squared divided by 2. D beta is minus d gamma. I have a negative sign and the limits are 1.5 to 0, so I can use them to flip it and write this is 0 to 1.5, 1 over square root of 2 pi e power minus gamma squared over 2 d gamma. So this integral is equal to this. So this is like writing 0 to 1.5 plus 0 to 1. So that is one more possibility here, where you have fourth possibility, minus d less than x plus e. So for your exam, that is both the third and the final or comprehensive, all I am looking for you to master is the ability to read this chart and to do problems. if you can make that connect, you will understand that these are all nothing but probabilities. Probabilities always are between 0 to 1. So if you multiply them by 100, you get a number that is like a percentage. Or if you multiply it by the size of the sample, you can project it for a population. Meaning, suppose the probability here, suppose here, you get a probability of say 68%. And your sample size was 200,000 people that you interviewed to collect a certain data. How will you project it back to the population?
Divide 68 by 100, what 200,000.
68 divided by 100 multiplied by 200,000. That is, you have to project it back to the size of the population, which you will be able to do. So instead of trying to state the obvious, all I want to get for you to get is the ability to read this chart, and later hopefully you would apply your thinking. Big hope, but I'm sure you come to. Okay. I mean, this is where they are just applying common sense logic. Okay, if you know how to do the math, everything else is something you should be able to carry forward. All right. So now I told you that we'll get you some explanations for what is 6 sigma, what is 1 sigma, and so on. Okay. So I want you to look at the chart and tell me the value, tell me the value of the area or the probability between -1 and +1. Look at this table and evaluate -1 to +1 for me. I want you to evaluate -1 to +1, 1 over square root of 2 pi, exponent of minus beta squared over 2 d beta from the table. You can write this as -1 to 0 plus 0 to 1. You can, right? Just splitting the integral into two parts, -1 to 0, 0 to -1 plus 1. So this part here, this is this part, and this is the right answer. What did I tell you? To hold this thread and flip the page. Okay, so this integral is nothing but 0 to 1 of the integral. So this is in effect 2 times 0 to 1. And how do you get 0 to 1? 0.3413. 1.00. 0.3413. Yeah.
Why do these other columns exist?
They are just like, if you want to know what is the value at 1.01, 1.02, 1.03, and so on. It's just like your steam tables, additional decimal points. Okay. So 0.3413 multiplied by 2 or 0.6826, or this is 68.26%. This number 68.26 and 1 plus minus 1, they have a connection. In the previous page, you had the picture. You see here, 68.26 lies between mean minus 1 standard deviation and mean plus 1 standard deviation. In a real system, the standard deviation and mean, they have units. But if you scale them and just say, if I normalize everything by the mean, within 1 standard deviation, I have 68.26% of the values will fall. Within 2 standard deviations, you can check this from -2 to +2, you can check this. you will get 0.9545 or 95, nearly 95% of the values within 3 standard deviations. And of course, this table here, its resolution is not, or its limits are not high enough for you to actually compute x minus 6 sigma to x plus 6 sigma. If you do that, you will get 99.99999. That is 1 millionth short of 100%. That's why that protocol is called 6 sigma protocol. Okay, 1 in a million short. So, you have a question? So what we are going to attempt now is trying to use all this knowledge we just received to solve this problem where a professor grades students on a normal curve. Clearly, that's not me. For any grade, based on a course mean of mu and a standard deviation of sigma developed over years of testing, the following applies. For x greater than mu plus 1.6 sigma, A grade is given. Between mu plus 0.4 and mu plus 1.6, a B grade is given. And between mu minus 0.4 and mu plus 0.4 sigma, C grade, and then D grade, and then F grade. So this class doesn't have a cutoff at 60% or something. The bottom percentile will fail. Doesn't matter if all of you got more than 60%, but according to this model, the bottom will fail. And many universities have such systems. Some courses will say the bottom 5% will fail. Even if they got 75%, the instructor might think that is worthy of fail. But that is all what instructors think, what is failing, what is passing, etc. But at least these equations say the bottom will fail. Okay, that's what you should take it. Question is, how many A, C, and D grades are given per 100 students? Express your answer rounding down to the nearest integer. Rounding down to the nearest integer. Before we solve it, what would be your strategy? What does this represent first? X greater than mu plus 1.6 sigma.
Like our x greater than C case?
It's like our x greater than C case, that's correct. The step before that is important, which is so I'm going to turn off this projection and make sure this gets recorded because it's an important point. I'll come back to the projection. Okay. So you been doodling with this bell curve, the standard normal distribution. And remember, it is constructed under a very specific assumption. What is that assumption behind this bell curve, behind this particular table?
Version of this, that's your bell curve.
Sorry.
Is it that when we have version of this, that's your bell curve?
So if you have any data and it follows a normal distribution, we write this is sigma x times square root of 2 pi exponent of minus 1/2 x minus x bar over sigma x squared. This is the normal distribution. Okay, normal distribution. Write this down. Okay, important stuff. So this x bar and this sigma x come from the data. And at the start of the lecture, we wrote this down as what is called as the population mean and population standard deviation. Okay, this is for any data set. All right. The chart that we saw, is for the so-called standard normal distribution, which is a special case with mean equal to 1 or mean equal to 0 and standard deviation equal to 1. A mean equal to 0 and standard deviation equal to 1. And for that, we do the lookup. We say A to B 1 over square root of 2 pi e power minus beta squared over 2 d beta represents the probability of z equal to x minus x bar divided by sigma x, taking values between A and B. Now I made a big leap here. Take a pause from the writing. I'll let you continue. But what I'm saying here is, when you are presented with any data, you know how to compute average and standard deviation. If you take that average and standard deviation, say your random variable or the quantity that you are trying to model, let's say that variable is x. Define what is called as the standard random variable. That is, the process of adding this word standard means you take z, call it z, you take x minus x bar divided by sigma x. What that will do is it will reduce any distribution to the standard normal distribution. So any problem that we present, it can be inspecting bulbs in a factory where you inspect hundreds of bulbs and from that you get a mean and standard deviation. You can reduce that into a problem that involves the standard distribution by applying this transformation. Now, how does that connect with our example? I'll let you write this down and I'll work out the example for you to see that connection. So in our example, x is score, okay, mu is mean or average, and sigma is standard deviation. Okay, so for if you look at the A grade criterion for A grade is what? That x must be greater than mu plus 1.6 times sigma. Take a pause, don't write. Okay, look at this. X, the actual score, like whatever your course total or a scale percentage of the course total, something has to be average plus 1.6 times the standard deviation. So if I define z equal to x minus mu divided by sigma, okay, what will this inequality become? This will become x minus mu divided by sigma should be greater than 1.6 or z must be greater than 1.6. So that is, this is in terms of the standard normal distribution, which is obtained by doing this simple transformation. So this is like asking, what is the area under the curve beyond 1.6 and up to infinity? You know to answer that question, don't you? What is the area under the curve beyond 1.6 and up to infinity?
0.5 minus area from 0 to 1.6.
That is, yeah, right. 0, that is 1.6 to infinity, 1 over square root of 2 pi, exponent of minus beta squared over 2 d beta. This is 0 to infinity, minus 0 to 1.6 or 0.5 minus 0 to 1.6, which you can look up. Now I have to bring back the screen for you to actually look up. So you look up the table and tell me. Oh. So what is the value of 0 to 1.6 from this table? Correct. Is everybody seeing that? What is the value of the area between 0 and 1.6? 4452. So everybody is able to read the table, right? So you just have to read the problem. There is a couple of steps. First step is reduce the problem from a normal distribution to the standard distribution, standard normal distribution, and then use the table. Okay. All right. So now everybody can think that you are saying this is 0.4452. You're good. Good. All right. So then. So we have, okay, 0.5 minus was it 4452?
Yes.
So what is that now?
0.0548.
0.0548, that is a fraction, and it's like saying 5.48% of the class will get A grades. And if the class size is 100, that is 5.48% or nearest to the lower smallest integer, that is 5 A grades. Right. 1 second. 5.48% or 5 A grades. Before I come to you, is this making sense? We got this fraction which represents the percentage of the class receiving A grades. You multiply that by the class size to get the number of A grades. If the class were 200 students, what would you do? You would take 0.0548, multiply this by 200, which is what? 96, 10.96 persons, and if I round it to the nearest lower integer, that is 10 A grades. But if it were 300 students, probably you will get like 16 A grades because of the small fraction that adds up. Yeah. What was your question?
How do we know that we can turn x minus mu divided by sigma into x? I don't know that.
Definitely equation, the A grade equation.
No, this is not something we know. What we are trying to do here is how it's like you ask yourself the question. I have the standard normal distribution worked out and computed as a table. How do I reduce every problem to that? And you do that using this transformation. It's like scaling. So suppose we are doing a problem of heights, and our average height in this class is like 5 feet 8 inches. You would take the average, subtract it from each value, and divide by the standard deviation, so that everything is now reduced to the normal form. Then you can use the tables to do all your calculations. Finally, you project it back. That is, you convert it back to the actual units. As practice, yes.
If it was 5.55, would you round up to 6 students?
No, the problem clearly said round down to the lower integer. It didn't say nearest, it said lower. Okay. So you have to read the problem and see what it says. So the other question is, oh wait, I need to stop this and make sure the camera gets this, because I was talking with the screen share on. So hopefully my narration in the previous minutes and this number will make sense. So 5.48% multiplied by class size, which is 100, gets me 5.48%, which doesn't make sense, which is equal to 5 acres. So now, let me bring back the screen. I want you to try. Want you to try. How many C grades will be posted in this class if the score lies between mu minus 0.4 sigma to mu plus 0.4 sigma, the grade is a C. So how would you transform this is by saying C can also be minus 0.4 less than or equal to x minus mu divided by sigma to plus 0.4. That is, I'm transforming this statement into the normal form, and this x minus mu over sigma is what we call as z, which you look up in the provided table. So it's like asking if the standard normal variable is between minus 0.4 to plus 0.4, that is the area of interest here. So how do you calculate that area? So this is between minus a to plus a. This is nothing but 2 times 0 to a. 2 times 0 to 0.4. So whatever 0.4 is, 0.4 has a value. That is the area between 0 and 0.4 is 0.1554. So minus 4 to plus 4 is nothing but 2 times, minus 0.4 to plus 0.4 is 2 times 0 to 0.4, which is right here 1554. So that is 2 multiplied by 0.1554, which is what, like 0.31 something, right?
3108.
3108, thank you. And for 100 students, that converts to 31 C grades. That converts to 31 C grades. Now, some other class, not our class. So, to quickly wrap it up, because we are near time and I need to distribute your exams. How many D grades? So D grades is like asking the x value lies between mu minus 1.6 sigma and mu minus 0.4. So this you can write, if you transform, this is like writing D is when the scaled value or the standard normal variable has a value between minus 1.6 and minus 0.4. That's interesting. Both are to the left of 0. Yes.
The 0 to 1.6 plus 0.
It's like you put your hand, flip the page, everything becomes to the right. So that is like asking what is the area between 0.4 and 1.6 on the right side. So this is nothing but the value area at 1.6 minus the area at 0.4. Easy enough to look up. So what is the area at between 0 and 1.6? 0.4452. I just want to make sure that everybody is able to look up this. And what is the area between 0 and 0.4? That is 1554, right? Yeah. 1554. So 0.4452. 0.4452 minus 0.1554, which is 8, 9, 8, 2, right?
Yep.
28.98, which if I multiply by class size, so 0.2898 multiplied by 100 students equal to 28.98 or 28 D grades. Yes.
So we're on like, if we're thinking about on the left side of the graph, and we're considering the area.
From minus 1.6 to infinity.
Yes,
It is just 1 point, it's the mirror image, 1.6 to infinity.
Thank you.
So for F grades, we want everything that is lower than minus 1.6. So that is like asking everything to the right of 1.6. Okay. So that would be, you can go home and check this. F grades would be 0.5 minus, what is the value for 1.6? 0.4452. Oops, sorry. 0.4452, which is 8, 4, 5, 0. So that is nothing but 5 students getting F grades. Yes.
On the exam, if we're given, the range and want us showing us substituting Z in and doing that.
Yeah. If you can show that one line, that will be very, it will help me understand that you got it. Yeah. So just hold on, one last point. The second part is what should be the lower and upper ranges so that approximately 0.4%, sorry, 40% of the class receives a B grade. That is, how will you solve for Y1 and Y2 such that the 40% of the class gets a B grade? This is the problem in reverse. You are told the area under the curve and then asked to look up what value will get you 40%. Okay, find 0.4 on the chart, but the problem here is you can do this in many ways. That is, if you look through the chart and find 0.4, so suppose here is 0.3997, I'll call it close enough. That is 1.28. Okay, so 0 to 1.28, if you set it, that will give you 40%. You can also look up 0.2. That is, you can look up where 0.2 appears, which is say here 0.553. So this value here is also approximately 20%. So twice of that is 40%. So think about it at a little bit. What I'm going to do is tomorrow at the recitation session, I really hope at least one person shows up, which if they do, I'm going to do examples on statistics, including this problem, and I'll post the recording later in the day. Okay, so this solution will come to you by tomorrow. And please work on your homework. Yes.
There's a Z table on that, I know.
Yeah.
yes.
Yeah, right here. All right, so the TA is going to hand out your attention, please. TA is going to hand out the exam. Tomorrow from 9 to 11:30, he'll be available to distribute homework 3. Yeah.
Where are we supposed to start?